Good morning, class. We are looking at chapter 1 review functions and models. We're going to also look at the review for a portion of chapter 2 for the sake of the first exam. This is being recorded. Okay. I ask you to please mute everything, audio, video. Okay. Do not put anything in the chat. In fact, for now, you can even change your name to your initials. If you like, at the end, when we are done and when I stop recording, I will ask you to put your full name. But for now, this is being recorded. So here we go. All right, so let's look at the examples that you see are all in the PowerPoint lectures that I have offered you already, and it's posted. We just want to quickly recap a few of these questions. So first, the description of a function, various ways, okay, verbally, numerically, visually, algebraically. And then the concept of increasing, decreasing, which one easy way means when x goes up, y goes up. That's increasing. When x goes up, y goes down. That's decreasing. That's as simple as that. And then we have an even and odd function definition. Okay, even, simply put, f of minus x is f of x, and odd, f of minus x is minus f of x. In the case of an even function, it's symmetric with respect to the y-axis. In the case of an odd function, with respect to the origin. So we want to find the domain. Anytime we are dealing with the domain of a rational function, basically the domain is all real numbers except what makes the denominator 0. So x can't be negative 2. However, if you were to graph it, it is important to understand the graphing requires, putting it in its lowest term. So x minus 2, okay, x cannot be 2. So in other words, x plus 2 is 0. Okay, so this is, you set this one equal to 0 and results in x equals 2, and therefore x can't be 2 is your domain. Now, what I want to add here, class, is the interval notation for that. So x can't be negative 2. What does it mean? Minus infinity, minus 2, union, minus 2 to infinity. Notice we are using parentheses at the end. Okay, class, we are using parentheses at the end, and that's extremely important for everybody to follow. Okay. For x cubed minus 5 over x squared plus 3x minus 10, in order for you to come up with the domain, you have to find what makes the denominator 0. Therefore, you factor the denominator. Now, the first one basically says x can't be negative 5. And the second one says x can't be 2. And again, writing this in an interval notation looks something like that. Okay. And that's extremely important. Okay. Now, how about this one? Are these two functions the same? And that's the idea, to make sure we understand the difference between this function perhaps and what becomes of it if we simplify it. So the idea is, if you look at the right side, okay, class, if you look at the right side, it is a line y equals x minus 2. Everybody knows how to graph it. Pick up a couple of pairs and graph. Okay. But when we go through factoring, and it becomes x minus 2 if x is not equal to negative 2. Okay, so no, they are not the same. What is the difference? The difference is, if I want to graph the rational function, that creates a hole at x equals negative 2. And that's important for everybody to know, okay? So in other words, it looks, so this is not to scale class. Okay, so something like this. Let's assume this is 2, 0. Let's assume this is 0, -2, and this is a graph of a line y equals x minus 2. However, for this function, so for this function, we have the same thing. Let's just graph it here. We have the same thing, but remember, x can't be -2. At -2 here, and this is not to scale, this point, there is a hole. With coordinates -2, negative. Okay, we've said too much. Let's quickly move on. All right, we want to see whether the function is even or odd. It's very simple. Just evaluate f of minus x, make a decision. So we're going to go through that. The first one, f of minus x will result in the same thing, but negative, the opposite of that. So it seems to be an odd function. On the other hand, if you look at part B and replace the x with negative x, you basically end up with the same function. That seems to be an even function, therefore. I hope everybody's comfortable with the concept. Okay, it seems to be an even function. Okay, and the last one you plug in, what happens? It doesn't look like the original function. It is not the opposite of the original function either. So it's neither even nor odd. Okay, now one quick look that can give you the answer is the following. If you look at this one, both of them are of degree odd, therefore ends up being an odd function. In this case, both of them are of degree even. Remember, one has degree 0. Okay, any constant, any number, any constant has a degree 0, therefore both of them are even, and the answer is even. But this one is mixed. One of them is odd, one of them is even, therefore it doesn't become any of the above. And that's really the idea behind this. I hope everybody's comfortable with that. Okay. Okay. We have a function. Okay. We wanted to see where the function is increasing, okay, decreasing, and a constant. Okay, so let's look at where the function is increasing. Okay, so that's where the function is increasing. Okay, where is the function decreasing? In other words, if you were to think of it as a line and it's not, does it look like a line with a positive slope or negative slope? If this was a line, this looks like a line with a negative slope, or a tangent line at any point gives you a negative slope. The same thing here. Okay, so this portion, and therefore that finally over here, it's a constant. Now, as far as the endpoint is concerned, depending on the text, I think most of the time your text takes them to be included, but it's really not a good practice. All right, let's look at an example of a linear function or a word problem or a math model, okay? As dry air moves up, it expands and cools. If the ground temperature is 20 degrees centigrade and the temperature at a height of 1 kilometer is 10 degrees centigrade, express the temperature, okay, as a function of h. And then draw the graph. I'm assuming everybody can do the graph. And what is the temperature at a height of 2.5 kilometers? So what matters is that I hope everybody remembers that basically in order to come up with the equation of a line, you need two things. You need one pair and the slope. If you are given two pairs, that works out the same way, okay? So remember, generally speaking, we go with X and Y class, X comma Y, but now we are going to go with H comma T, okay? Why is that? Because T is a function of H. In other words, right away, if I were to look at this, I would say this means T of H. Remember, let's go back to, remember f of X? F of X, of course, is normally Y. You follow what I'm saying? T of H. So it makes H the independent variable T, okay? The H, the independent variable, and T is the dependent variable. T depends on H. You could have it the other way around, but this is the way they want it here. And so we use delta Y over delta X, rise over run, and we are going to change the Y accordingly. So first write this formula that you are familiar with, and then the Y's are, T's and X's are H's simply because of the dependency and independency, and you come up with negative. And as you recall, okay, for the sake of f of X, if you remember, Y equals mx plus b when we have, okay, you remember, I'm going to put it up here. Y equals mx plus b if the y-intercept is given. So in this case, we do have 0, 20, so we don't have to go through y minus y1 equals m times x minus x of 1 accordingly, of course. I'm going to assume everybody can graph it. I wouldn't worry about that. And then the last part, basically, you replace the h with 2.5. Okay. By the way, the slope, if you want to see what it represents, okay, minus 10 degrees centigrade per kilometer, it represents the rate of change of temperature with respect to height. If you remember the way we defined slope, the average rate of change of y with respect to x. Of course, we are changing y and x accordingly, okay? We are changing it accordingly. So that's why this definition is in order. The next thing I want to show you is that translation. Okay, I hope everybody remembers this is basic translation. I don't, dwell on it too much as long as you know the basics. You're fine. You've seen it in algebra, in pre-calculus. You should be fairly comfortable with that. So basically, given a function f of x. Okay, so f of x plus c takes it up by c units. Minus c brings it down by c units. We are assuming c is positive, and it doesn't have to be. But if it's inside x, f of x minus c shifts it to the right, f of x plus c shifts it to the left by the same amount. Then if you have f of x, okay, if you so if you have f of x, okay, and you multiply it by c, okay, you expand it by c, 1 over c. Again, we are assuming c is positive. It makes it as small. And of course, f of minus x, reflection with respect to the y-axis, minus f of x. Okay, we are comparing it to f of x, reflection with respect to the x-axis. The other thing that I want to add is that the domain of one function is a, excuse me, and the other one is b. Then when we look at the algebra of functions, this is algebra of functions, right? The sum function, the difference function, the product function, the quotient function. The domain would be the intersection of the domain for all of them, okay? In the case of the last one, f over g, then you got to be careful. You don't want the denominator to be 0. Okay. let's look at this example, this concept also. What about the absolute value function? If y is absolute value of f of x, this is what happens to its graph, okay? And again, I want to remind you of definition of absolute value of x. Everybody knows that this is x. If x is larger than or equal to 0, and it's minus x otherwise, right? Basically, the same thing works for a function f of x. So translation from here to here, basically, if you're changing to f of x, the same thing happens. So, okay, what does it mean if you want to graph the absolute value function? Well, the portion which is above the x-axis is considered positive. You don't change it, but the portion below will flip over. Okay, so let's look at part A. The very first thing we do, we ignore the absolute value and we graph that. Okay, so, and how do you graph it? Y equals x squared is a parabola. Okay, minus 25 brings it down by 25. So that's x squared minus 25. We want the absolute value of that. This portion, the blue one, doesn't change because it's positive. But the yellow one below the x-axis will flip over. And this is your final graph, okay? We want to graph this. Let's go with the steps and ignore the absolute value and start with y equals square root of x. Again, elementary functions, we are supposed to know the graphs, class. Hopefully we all do. Okay. So we start with this graph, y equals square root of x. It doesn't have to be perfect. As long as it's close enough, that's good enough. Okay. We all know ultimately everybody has access to a graphing calculator, which can do a much better job, but you need to know a rough sketch of every elementary function studied. So with that being the case, so we have square root of x. Now, the second one, let's say y sub 2, is square root of x minus 1. So we take this one and we bring it down by how much? By 1. Now, this portion is above the x-axis and it's not going to change, everybody. But this is below. Now the last step is this absolute value. So this will flip over. Looks like that. That's your final answer. Okay, everybody? That's what we get. Okay. So the portion below the x-axis will flip over. Again, just simply because of this definition, if you will. All right. Let's quickly find the domain. We again remember the graph, and the domain is 0 to infinity. And if we call it A, for example, okay, 0 to infinity, okay, class. Then what happens in this case is 2 minus x greater than or equal to 0. And 2 minus x greater than or equal to 0 means, let me just write means 2 greater than or equal to x, or x is less than or equal to 2, and that results in this. Okay. Very straightforward. Okay, we got both of them. And now, what if we look at f plus g and f over g? I hope everybody knows f plus g by definition means f of x plus g of x. F over g by definition means f of x over g of x. So what is now the domain for this function is the intersection of a and b. How do you do the intersection? This goes from 0 to infinity. This goes from negative infinity to 2. I hope you realize that their intersection is simply 0 to 2. Okay. So if you have any doubts, you can graph both on a number line, class. Just maybe So this is from 0 to infinity. Okay. Whereas this one is from 2, if you will, okay, to the left, right? So I hope you see that the green and the red come together from here to here, which is 0 to 2. Now, what happens for part D, again, we have the same thing. But there is a restriction, and you just have to look at the denominator. The denominator has this part, and it can't be 0. 2 makes it 0, therefore 2 is out. So I hope you see what happens. Practically, for most part, we have the same thing. We just want to get rid of whatever makes this denominator 0, and that's the idea. Okay, that's why this has a bracket around 2, but not here. Okay, how about f, g, and h given? Finding f of g or h, we can do it a couple of different ways. One of them is just ignore this part, find f of g first, which is f of g of x, f of g of x. So with the f, replace this x with x squared. So that's f of g. Now composite or compose that with h, f of g o h, which means now what is h? X cubed plus 6. Now replace that. Okay, so you get x cubed plus 6 to the power of 2. And that's your final answer. So that's simply done by inspection. All right, so combinations or algebra functions. A lot of exponential formulas, I hope everybody remembers them, okay? A to the power of 0 is 1, a to the power of m times a to the power of n is a to the power of m plus n, and the rest of them negative exponential, so on and so forth. So there are a lot of exponential rules. We've seen them in elementary algebra. We have no problem with it, okay? Now, what about an exponential function of the form b to the power of x? It really depends on the value of b. B can never be really 1, because when b is 1, when the base is 1, you don't have an exponential function. This is not an exponential function. This is a horizontal line. When it's between 0 and 1, we have an exponential decay. When you have it larger than 1, becomes an exponential growth. Therefore, if I'm graphing, for example, 2 to the power of x, I look at this one, roughly. If I'm graphing 1/2 to the power of x, I'm looking at this one, roughly. Okay, and by the way, horizontal asymptote, the x-axis, okay? The x-axis has the equation y equal to 0. Vertical asymptote, we don't have any. Y-intercept at 0, 1, okay? X-intercept, we don't have any. Domain, all real numbers. Range, above the x-axis, only 0 to infinity, okay? Now, when b is positive, okay, you're looking at this one, then it makes it an increasing function. When it's negative, so this is common between the two. And this is increasing when the base is positive, and decreasing if the base is between 0 and 1. Let's look at an example of that. We are given the following, we want to graph, and again, start with what you know. You really have a choice. Go back to it. You can say, I'm going to go with that, or I'm going to go with that. But when we say, by the way, 1/2 to the power of x, let me just write this for you just to remind you. If by any chance you are looking at this one and say an example of that is, 1/2 to the power of x. It's the same as 2 to the power of minus x. I want you to know that, okay, everybody? It's the same. But anyways, starting with the basic, so we're going to start with e to the power of x, and e to the power of x looks like 2 to the power of x or 5 to the power of x, and so on and so forth, okay? So we're going to go with a couple of steps. Now, we are going to change this to e to the power of minus x. If you change the x to minus x, it flips over, okay, with respect to the y-axis, and it looks like that, okay? Now, 1/2 basically compresses it a little bit by a factor of 1/2. So for example, 0, 1 is here, okay? Now it becomes 0, 1/2, okay? So now it's 0, 1/2. So maybe we write this. Okay, so this has coordinates 0, 1. It has changed to 0, 1/2. And finally, finally, this -1 brings it down by 1. When it shifts it down by 1, it looks like this. Okay. So now your point here, let's just, the point 0, 1/2 now has coordinate 0, -1/2. Okay. And that's a graph. And as you can see, the domain is still all real numbers. The range has changed from 0 to infinity to -1 to infinity. And it is a decreasing function. It has a excuse me, horizontal asymptote of y equals -1. So there are some changes that has taken place. Okay, everybody? Okay. We want to come up with a domain. You can ignore what you have underneath if, in general, you remember square root of x, x is greater than or equal to 0. I hope you remember that. Square root of x, x is greater than or equal to 0. And basically, you're going to work on this. This is how you come up with this domain. So 10 to the power of t, okay, is larger than or equal to 0. So, okay, so the order sadly is not the way I want it to be, but that's fine. Let's just discuss that one since it came up. This is sine, never mind, that's, imagine it's sine x, okay? Sine x is, the domain is all real numbers. Then if you happen to have anything other than x, you look at the argument of sine, and this has no restriction. As you know, exponential functions, or e to the power of t, and also e to the power of t minus 1, the domain is all real numbers. So you say sine, this is a composite function of sine and exponential function, the domain is all real numbers. But continuing on these thoughts, okay, so we move the 100, negative becomes 100 on the positive 100 on the other side, okay? And we know 100 is 10 squared, then t must be larger than or equal to 2. So take a look at this. This is the exponent. This is the exponent. And if it wasn't 100 class, you would have to take a root of that. Let's make it up. Let's say it was number 50. Then this would, the base would be square root of 50. Okay, the power of 2. That's the idea. But it won't work with this one. It is set up that it will work with this base. Okay, I have to somehow come up with that. Now, in this case, we want to solve for t. So basically, combine the left side into one exponential functions, okay? And as you can see, this is a product rule, the product of this and that, e to the power of this exponent plus this exponent. That would be the left side, yes? That would be the left side, everybody. And what happens is, basically, you're going to say t is the exponent. It's that simple. I hope everybody is comfortable with that. There is not much to it, class. Okay, there is not much to it. So I hope everybody is comfortable with that. Okay, we are ready to move on. As far as the logarithmic functions are concerned, there are a lot of formulas that we are supposed to know. There are a lot of properties, but the most important one is the definition. And that is, understand that log is simply an exponent. If we understand that, we are home free, okay? Log is simply an exponent, okay? So just for the sake of argument, if I'm interested in the following, if I say 2 to what power is 8 is the same as saying log 8, okay, base 2 equals what? And in both cases, obviously, so as long as we understand the definition, we are in good shape. So in both cases, the answer is 3, okay? So what is log is simply an exponent, and it gives rise to the following properties. For example, here, b to the power of 0 is 1, b to the power of 1 is b. These two refer to the fact that the two functions, that means log and exponential functions, undo each other, okay? And this is the product rule, quotient rule, and the power rule we should be comfortable with. Now, the same thing, if you go with common log, we use log, no base means common log. That's the meaning of it. And therefore, the definition becomes 10 to the power of y equals x, okay? We can write the natural log. When we write ln, that means the base is e, okay? And we are using the same properties. This is general, this is specific, okay? We also have the graph where the logarithmic functions and exponential functions are inverse of each other and therefore symmetric with respect to the line y equals x. And it's important to understand that an example of that would be y equals e to the power of x, y equals ln x, okay? It could be y equals 10 to the power of x and y equals log x, okay? Obviously, according to the graph, okay, when you're looking at this portion of the graph, the y coordinate is negative. So that's why when x is between 0 and 1, the y coordinate or ln x is negative, okay? Precisely, it's at 1 is equal to 0, and then beyond that is positive. So this comes just from the graph. Look at the graph. This is the result of the graph. There's really not much to it, okay? And of course, the change of base formula, we need this later on for differentiation. You've got to be very comfortable with this page when it comes to differentiation class. We're going to need this, and you'll see that, okay? All right. And of course, if functions are inverse of each other, their composite function is x. All right. We want to find the inverse function, so let's go through the process. There are different ways of approaching it. One way is this. Number one, change f to y, just because it makes life easier, okay? Now, you have a choice, okay? You can solve for x and then interchange, or you can interchange x and y and then solve for it. Either way makes no difference. So let's interchange x and y. All we did, we changed the y to x, x to y, and right here we do have the inverse class. However, we always solve for y. So how do you do that? Do the cross product. So if I do the cross product, x times 2y is 2xy, x times 3 is 3x, and 4y, and this is, let me just write this as over 1. Okay, so cross product, okay? So that's what you have, okay. Since we are solving for y, we have a choice. We can use, we can move this one to the right or this one to the left. It doesn't matter. Okay, why am I moving them in this fashion? Because since this is -1, if I move the 3x, then I have too many negative signs. It doesn't matter. And at this point, basically the right side is y times 4 minus 2x. So you put 4 minus 2x as the denominator for the left side. There you have it, okay? So you give it the name f inverse. By the way, if we had moved it differently, okay, we would have had in this fashion. If this was, okay, this is another way of writing it. If we had moved it differently. Understand the two are the same, but I wanted to use the least number of negatives. And you are really not done. You have to show that their composite function is x. So I'm going to leave it for you to do that. All right, let's look at this example. Okay, we are going to write them as a single log, and the very first thing is to pay attention to piece by piece. 1/3, you take it in, becomes ln of x plus 2 to the power of 3 times 1/3. So they cancel each other in essence. Remember, this is the reverse process of the power. 1/2 ln x, that means ln x to the power of 1/2. And then 1/2 inverse. So this takes a 1/2 also. And this 1/2 and 2, they go up there and they cancel each other. I don't know if you are following that, but let's just quickly do it as follows. I can take this to the exponent and they cancel each other. I can take this to the exponent ln of x to the power. So this becomes ln of x to the power of 1/2. Then minus. Now I have a 1/2. Now this 1/2. Okay, 1/2 ln of this, right? And now I put the 1/2 at top. I put the 1/2 at top. With the 2, they cancel each other. Okay, so that's the idea. All right, now what do we have? We have ln of this times this, and this is negative, this goes down. But let's factor this. This is x plus 2 times x plus 1. So x plus 2 is at top, x to the power of 1/2 or square root of x is at top, and this one is at the bottom. In factored format, x plus 2 cancel each other, everybody. And that's your final answer. Okay. I hope everybody's clear on that. This is really not much. This one, first and foremost, we're going to put this up here. Okay. And then we're going to multiply this. So this becomes ln of x plus y times anything that has a positive coefficient keeps at top. The next one has a negative, so goes down. And then you write it as such because x plus y times x minus y is x squared minus y squared. Okay, we want to expand this. Okay, so it's the reverse process. We are going to write this as a log of this mess to the power of 1/2. The next step is to put the 1/2 in front, everybody. Put the 1/2 in front, and it's 1/2 of this log, and then expand it as log of the top minus log of the bottom. So I hope it's clear to everybody. It's pretty straightforward, everybody. There's really not much to that. Logarithmic functions, we need to expand them. We need to put them together. We need to be familiar with that. Okay. We want to find the inverse function for something a little bit involved. Okay, I figure, you know, something involved from pre-calculus, we can look at it. And obviously the first step, you know, we change the f of x to y. The second step, we said we're going to interchange x and y. So those are, you know, basic. Now we are going to do the cross product, everybody. One times this, x times this, okay? So when we do the cross product and we distribute, we get x plus x e to the power minus y on the left side. Okay, remember, the purpose is to solve for y. And in order to get to the y, remember y is the exponent here. In order to get to the y, Okay, let's see what we can do. Okay, this is e to the power of minus y, and if you want, class, you can write it as 1 over e to the power of y. You can do the same thing. If it helps, let me write that top of it. If it helps, change each one of them to 1 over e to the power of y. If it helps, see what you have. So it makes sense when I say I'm going to multiply everything by e to the power of y to get rid of the denominator. So when you do that, let's see what happens. I want to make sure everybody understands what happens. So this one times e to the power of y. This one, let me write it underneath, just this one, because in case, so this, just this one, okay, becomes x e to the power minus y, e to the power of positive y. E to the power of minus y and e to the power of positive y becomes e to the power of 0 or 1, and this whole thing becomes x. And the right side, 1 times e to the power of y minus this one times e to the power of y is also 1, so minus 1. Okay. On the left side, we can take out, we can combine the e to the power of y by bringing this to the left side, and then on the left side, we can factor out e to the power of y. Okay, so we did that. So e to the power of y is the right over the left. By the way, notice this has negative sign, negative sign. This is the same as multiplying by -1 and multiply the bottom by -1 becomes, minus x plus 1. So multiply the top by -1, you get x plus 1. Multiply the bottom by -1, we get minus x plus 1. Okay. And of course, the top, because the bottom is 1 minus x, maybe we want to write this one as 1 plus x instead of x plus 1. Not that it makes any difference. So how do we go from here to y? Take a natural log of both sides. If I take a natural log of both sides, ln of the left is ln of the right. The left side becomes y. And that's f inverse. Okay. Again, I leave it for you to look at their composite function. That would be really interesting for you to do. Okay. All right, we want to solve a couple of equations. It's generally speaking, logarithmic function. All you have to solve this, go by definition. Okay, definition of a log. So the base is e cubed is the argument. E cubed is the argument. Okay, so x squared is 1 plus e cubed. So x is plus minus the square root of that. It's pretty straightforward. If you can't see the factored format here, which is this one, you can change it as follows. If it helps, let e to the power of x be, for example, y. Therefore, you're looking at y squared minus 3y plus 2 equal to 0. And you factor this to y minus 1, y minus 2, and it gives you that. And the rest is simple. E to the power of x is 1, and that means x is ln 1, okay, which is 0, and e to the power of x is 2, that means x is ln 2. And you keep it precise as such. One thing I want to add, class, and you want to be very careful of, if by any chance we had e to the power of x plus 1, then e to the power of x becomes minus 1, and that doesn't have any solutions, okay? So you want to be careful with that. So ln of whatever the argument, you can even ignore that. Imagine it's y. So y is e to the power of 1. That's it. Never mind what the argument is. Ln of something is 1. So e to the power of 1 is that expression, okay? And of course, e to the power of 1, we know it's e. Therefore, we do it again. Ln x equals e. So what is x? The base is e, e to the power of e. E to the power of e is the answer. Okay. How do you solve a case like that? By division. Okay. Divide, okay, keep the c, divide by e to the power of bx. Now, when you divide, this expression, class, is equal to c, and this expression is the same as e to the power of a minus bx. I want to make sure everybody understands why this is the case. This expression, everybody, is the same as e to the power of ax minus bx. Okay, the quotient rule for exponentials, which is a minus b times x. Okay. And so remember, we are solving for x. Let me change this again. So if you take a natural log of the left side, or you go with the definition of a log, either way. Natural log of the left gives you a minus b times x, and the right side is just ln c. And now dividing by a minus b gives you the x. Dividing by a minus b gives you the answer. So we are looking at equations that are different than some of the stuff we are used to. Here's another equation we want to solve, and to solve that, it's a good practice. Anytime you have a logarithmic equation, to solve a logarithmic equation, bring every log to the same side and the numbers to the other. If all of them are logs, then it really doesn't matter. Just bring it to a single log. In this case, we're going to move this, becomes plus. We're going to combine these two into one log. And now that we have nothing but one log on one side and a number on the other, we go with the definition and we say this is e squared. We write this as 2x squared plus x equals e squared, and there's nothing we can do. It's just a quadratic function. We bring e squared, and remember, bear in mind, e squared is a number class. This is a number, but it's a, if you go with the decimal, it's a nasty number, but just keep it as it doesn't make any difference. It is a number, and that's important to understand. So we are going to use a quadratic formula. If we are going to use the quadratic formula, then a is 2, b is 1, c is negative e squared, okay? And so x equals minus b plus minus the square root of b squared minus 4ac over 2a. So plug in minus b is minus 1 plus minus the square root of b squared, or 1 squared is 1, minus 4, okay, times a, which is 2, times c. So I can write at top of it if you want. Minus 4 times a and times c, and that's how you get plus 8e squared, okay? And so with that being the case, there are two answers. However, we only get the positive one because minus 1 minus that expression makes this one negative. And remember, going back to original one, this one says x must be positive, okay? This one says x must be larger than negative 1/2, okay? And so therefore, the negative part is out. There are two answers, the negative part is out. Okay. Let's look at this one. Cosine of sine inverse is this expression. So we start with sine inverse, and by definition, anytime you are dealing with, arc, sine, okay, or sine inverse or cosine inverse, or in general, trigonometric functions, inverse trigonometric functions, you let this one be alpha, beta, theta, gamma, or anything that you like. So if this is theta, By definition, therefore, sine theta is x. So if sine is x, cosine is plus minus the square root of 1 minus sine squared theta, because we all remember sine squared plus cosine squared is 1. So we know that, okay? And in this case, therefore, we are going to replace the sine with x. It's plus minus square root of 1 minus x squared, and we take the positive one. And the reason why, so again, replace the sine theta with x, and the reason we take the positive one, okay? Because y equals sine x is between negative pi over 2 to pi over 2, and cosine is positive. Remember the restriction. None of the trigonometric functions is 1-to-1. None of them has an inverse unless you restrict the domain, and the restriction on sine is from negative pi over 2 to pi over 2, the same as tangent follows the same thing. It doesn't have the equality, and the so therefore it makes it positive as far as the cosine is concerned, because cosine is positive, okay, in the first and the fourth quadrant. This is the justification for that. All right, we are going to look at this one. And again, if we wrote cosine inverse or arc cosine, it means the same thing. Again, we are going to go with that expression, if you will, and cosine theta is x, okay? And when we say sine 2 arc cosine x, that means a sine of arc, sine of 2 theta. Okay, sine of 2 theta, if you remember, is 2 sine theta cosine theta. Sine 2 theta is 2 sine theta cosine theta. This is one of those basic, you know, identities that you're supposed to know. I've gone over that in my PowerPoints. And so you replace the cosine with x, and what about sine? In essence, is the same as this one. If you go back, there's a 1 square root of 1 minus x squared, and the justification is the same in a sense that because cosine, remember, goes from 0 to pi, and from 0 to pi, sine is positive. So 2 sine theta cosine theta, I put the cosine first, 2x squared of 1 minus x squared. I hope everybody's comfortable with that. So again, pay attention to the domain and range. All right, so we are continuing with the exam 1 review that covers also a portion of chapter 2. So here we go. We are looking at chapter 2, which covers 8 sections. We're going to cover the first 4 sections. So quickly, I want to remind you about the concept of the limit. It is extremely important to understand what happens here. So let me put this in slide mode again and explain a few things. Number one, a limit, and the definition of a limit is that basically when x gets closer and closer to some value, okay, along the x-axis, for example, a, the functional value, the y gets closer and closer to some value, which is, we don't care what happens at a. It's not important what happens at a. And this limit only exists if the one-sided limit exists. In other words, the limit of f of x as x approaches a from the left is L, the limit of f of x as x approaches a from the right is L, then the limit exists and it's equal to L. Of course, this is the definition of a vertical asymptote, in which case, basically, if the function blows up to infinity or negative infinity, when x is approaching a from any side, a from the left or right, then the VA, short for vertical asymptote, is x equals. Now, here's the concept that is extremely important when it comes to a limit. What do we mean by limit? Remember, we don't care what happens at a, but what happens near a. So as we come towards a from the left and right, okay, along the x-axis, from the left, we are moving in this branch. From part of the graph, from the right, we are moving in this part. In both cases, we are shooting towards this point, which has a y-coordinate L. This repeats in all 3 cases, which means in all 3 cases, the limit as x approaches a is the same thing, which is a. However, let's discuss the differences. In this case, f of a, the functional value, is also known to be L, which means the function is continuous. And that's the definition of a continuity. However, over here, f of a is known, but it's not L. What is f of a? The y coordinate of this point, which is B. In the last case, what is f of a? We don't know. It's not given to us. It's undefined. Okay. So that is the extent of the similarities and differences. And if we understand this, we are extremely comfortable with the concept of a limit class. Okay. And I hope everybody is okay with that. Okay. So let's move on. We are looking at these functions, okay, the graph, if you will, okay, and we are interested in finding the following limits. So, number 2 class, we are really interested in this one. That's why we look at left and right. Number 2, from the left of it, we are moving this way. That means we are moving in this part. And as we move, we are heading towards this point, okay, which has a y coordinate, 3. On the other hand, from the right side, we are moving here towards this point, which has a y coordinate, which is 1, and it's different. So because they are not identical, the limit does not exist. So the limit for one side is 3, the other side is 1. Therefore, the limit of f of x as x approaches 2 does not exist. So again, why is that? Because they have to be identical. Okay. Okay. Now the next part says, okay, so what is then for f of 2? If you look at number 2, the solid point has the y coordinate 3, and therefore f of 2 equals 3. Oh, never mind. Let's discuss this one also. F of 2 equals the y coordinate of the solid point, which actually means this function is discontinuous at 2, but it's continuous from the left, if you will. That's what we are going to discuss later. When it comes to number 4, from the left side of 4, we're moving here towards this hole. From the right side, we're moving here, but still we are moving towards the same hole, having the y coordinate 4. So that exists, and it's equal to this y coordinate. But remember, we never get there. Now, what is f of a 4? We don't have a solid point, so I have no idea. It's undefined, okay? In order for you to answer that, you need a solid point, everybody. Since it's not given, we don't know. Okay, since it's not given, we don't know. All right, let's look at this case. In this case, class, we are given the function, the graph of a function, and we want to know the limit of this function as x approaches various numbers. So let's look at number 2. Okay, I hope you see that as we approach number 2 from both sides, it's going down to negative infinity. On the other hand, for 5, from both sides goes up to positive infinity, right? From the graph. Okay, negative 3 from the left, negative infinity. From the right, it shoots up to positive infinity. And according to this, obviously, then the vertical asymptotes, if you look at the first one, x equals 2, the second one, x equals 5, and this one, x equals negative 3. Okay, I just put them in the order that I received them, but as you're doing it, for example, in WebAssembly, they may ask you for a specific order. Okay, class, so you can stick with that. All right. Let's look at some limits, and we want to see how to deal with them. When it comes to limits, there are really 3 ways to deal with them. You can graph and look at it graphically. That was discussed, you know, in my PowerPoints. Numerically, that means, for example, in this case, you look at numbers close to 0 from the left and right, okay, and discussing. But we are mostly interested in algebraic method. So here's what's going to happen when you're dealing with limits. And you want to be very careful with that. Either you, and so we just plug in and we observe. Class, we just plug in and we observe. So we plug in and we get to a number. If it gives us a number, we are done. We plug in, it gives us 0 over a number. When I say 0 over a number, that means 0 over any number except 0. We are done. Check mark. It may give us a number, any number, some number over 0. Now what happens? Remember, when you have a number divided by 0, we used to say it's undefined, but that's not what we are saying now. It's either negative or positive infinity. Now, which one, you got to figure it out. And the reason you got to figure it out, because 0 is the only number that from both sides give us different signs. If you're approaching number 5, from the left and right is close to 5 and it's positive. If you're approaching negative 10, both sides close to negative 10, both sides negative. But 0, left and right have a different sign. But in calculus, most of the time, we get to the following cases. These are some of the cases we see, which is called indeterminate, such as 0 over 0, infinity over infinity, infinity minus infinity. And you have to approach it the way we have done it so far, whatever has been taught so far. And again, we cannot use something that hasn't been taught yet. I hope you realize when you plug in, you get 0 over 0, and the technique involved that was discussed in the PowerPoint was to multiply by the conjugate and divide by it. So it's simply put, multiply by the same thing changes to plus, multiply and divide by it. So first, understand you plug in, it gives you 0 over 0. You multiply by the conjugate. Now, it's important to know that you multiply and you divide, because this expression is equal to 1, and it is justified to multiply by 1. You can't just justify by anything you feel like it, okay, class? So it has to be 1, and that's why you multiply and divide. I can't emphasize this enough, okay? Okay, and so what happens when you multiply? The top, you're looking at a minus b times a plus b, which becomes a squared minus b squared. That means this comes out as x plus 4, and this becomes minus 2 squared, which is 4. Now 4 and negative 4 cancel each other. And now you get rid of the x, and numerator becomes 1. Now if you plug in the 0, you get 4, square root of 4 is 2, 2 and 2 is 4, so 1 over 4 is your final answer. Extremely simple, class, extremely simple. What's the technique? Multiply by the conjugate and divide by it. All right. What happens in both cases here, class? The numerator is -1 and the denominator is 0. And I was just discussing this concept here, a number over 0, okay? Any number other than 0, then the 0 in the denominator, you have to figure out it's negative or positive in order to come up with the sign. Remember, this will go to infinity, but we need to know is infinity or negative infinity. So how do you figure out from the left or right? You literally pick a number, -3 from the right. I pick up an example of that, class. -3 from the right, let's say -2.9 plus 3 becomes positive 0.1. That means -1 over 0 from the right. Negative over positive is negative infinity. How about this guy? -3 from the left, it's like -3.1. With the denominator +3 gives you -0.1. That means you -1 over 0 from the left. Negative over negative is a positive, and that's how you arrive at the answer. Again, this is the trick that will do the job. You don't want to add -3.1 and 3. You want to do that in your head, but understand why we arrive at 0 from the left or 0 from the right. Okay, that's the idea. Okay. Okay, here's some examples we want to do, okay, and understand what happens. You basically plug in and you observe. Anytime you have a rational expression, however, class, it's really a good practice to simplify. That means factor if you can. If you plug in, you get 0 over 0. As far as getting, if you don't get 0 over 0, that's a different story. But if you do get 0 over 0, the factored format, in fact, becomes fairly easy because x is approaching 4. Most likely, you have a factor of x minus 4. If it was approaching 10, you would have a factor of x minus 10. If it was approaching -4, you would have a factor of x plus 4. So take a look, you factor. So x minus 4 cancels out the x minus 4. And now when you plug in, you get 4 over 5. And you're done. It's that simple, class. Okay. Plug in. Clearly, you get 0 over 0. The technique, conjugate. Divide and multiply, both. This is equal to 1. So this is 0 over 0. Here's the technique. All right, the top 1 plus h comes out, and then minus 1 squared, which is 1. As far as the denominator, don't ever touch it. Keep it as a product. Now 1 and -1 cancel each other. You're left with h in the numerator that cancels out this h, and the numerator changes to 1 only. If I replace this h with 0, I get 1. Square root of 1 is 1 and 1, 2. 1/2 is your final answer. Part C, x is approaching 6. Just plug in everybody. If you plug in, this goes to 0. This is 3. Square it, you get 36 minus 7 times 6, 42 plus 12. Just plug in. Do the math and you end up with 1/2. In other words, you plugged in and it worked. Fine, we are done. So don't assume that you, I want you to compare this to this. Don't assume you have to multiply by the conjugate immediately. The reason we do that here, class, this gives you 0 over 0. And that's why you do that, okay? So I hope everybody is comfortable with the reasoning behind that. Again, you have here 0 over 0. What is the technique? LCD, which is 3x, multiply by 3x over x, 3x. Now the product of the denominator, again, this is how you change the complex fraction to a simple fraction. This is one easy way. This is the fastest way. Is this the only way? No. So what happens, class, it's very simple. You multiply the 3x by 1/3, okay? And you get x minus, you multiply it by 1 over x, you get -3. And the denominator, you just write it as a product. X minus 3 cancels out x minus 3. And practically, we are home free. We are done. Okay, everybody? Okay. The limit laws basically says if you happen to have a sum, okay, you have a limit of f of x as x approaches a, g of x as x approaches a. What about the sum? Separate them. Difference, separate them. If you have a constant, take it out. If you're multiplying, separate them. If you're dividing, separate them. All of the above. But, you know, like I said, these are limit laws. In general, we do direct substitution and we observe. This is referring to continuous functions. By the way, anytime we claim a function is continuous, we should be able to come up with its domain. For example, a polynomial function has a domain of all real numbers, okay? So functions with the direct substitution property are called continuous at A, okay? We have this squeeze theorem also, which is extremely important. If we have a function between two other functions, and what matters, it's in some interval of interest, okay? In this case, for example, near A. Doesn't matter what happens otherwise. And this guy has a limit. This guy has a limit. Both of them have the same limit. Then the one in between must have the same limit. This is called the squeeze theorem. So if the extremes, f of x and h of x, have the same limit when we go near A, then the one in between should have the same. Okay. All right. We are going to move on, class. And I believe we just had this done, so I don't want to spend time on this. Okay. I'm going to just show you again. I think I had made some changes here, class. So I'm going to just remind you about the previous page when we did the limits. Okay. And I just changed it accordingly. Let's go to the next one. Okay. We want to evaluate the following limits, see if they exist. And to come up with that, you are going to look at the graph and see that we have the red function, the f function, and the blue function, which is the g function. And for this one, okay, x is approaching -2. Okay. So let's look at -2. This is -1. This is -2. So for -2, the f function from the left and from the right are moving towards this point. This point having y coordinate 1. Okay. Now the blue one, okay, this is -2 from the left and right. They're moving towards the same point, having the y coordinate -1. So first and foremost, observe these two from the graph. After that, now this means we want separate them. We want this one and we want 5 of that one, class. We separate. And now we plug in. We got the information, plug in, everybody, plug in. So that means 1 plus 5 times -1, whatever the answer might be. 1 plus 5 times -1. Now, for this one, we want the limit of this function as x approaches number 1. Okay. So a quick, look at it. It tells you that if you're looking at the f function, the red one, 1, both sides of 1, left side and right side, brings you here, which has number 2 as the y coordinate. But 1 obviously is discontinuous. From the left of 1, we are here, giving us -2. From the right, we are here, which gives us -1. For this one, the limit doesn't exist. So the very first thing, notice this is the case. And I'm explaining why, okay? And because of that, this doesn't exist, class, okay? So the limit of f of x equals 2 as x approaches 1, but the limit of g of x as x approaches 1, there are two different answers, therefore it doesn't exist. So the product doesn't exist either. Now, by the way, I'm explaining what I just went over for the g of x, which is -2 versus -1. They must be identical. They're not. You can leave it as that. Because this doesn't exist, this doesn't exist. And that's good enough. I want you to know that. Also, you can evaluate this one from the left and right, class. If you were to do that, The limit of this function as x approaches 1 from the left is 2 times -2, and as x approaches 1 from the right is 2 times -1. Again, these two are different. So this is another way. Do you have to do this one? No. The moment you have this one class, the answer is this product doesn't exist, okay? How about this one, this limit of f of x over g of x as x approaches 2? Let's look at them again individually. Okay, so x is approaching number 2. So we have number 2 here. From the left and right of the 2, for f of x is this point, like, I don't know, 1.3 or 4, 1.5. Whatever you read is, I'm fine with that. But when you look at g of x as x approaches 2 is 0, because this is 0, you're dividing a number by 0, and therefore it's not defined. The denominator for this one, the denominator approaches 0, while the numerator approaches a non-zero number, therefore it doesn't exist, okay? That's how you arrive at the answer here, just from the graph. The top gives you a value, the bottom gives you 0, approaching 0, not doable. All right, let's look at this squeeze theorem that was discussed. Let's look at this squeeze theorem that was discussed quickly. This is a very simple case. We want to find the limit for this guy, g of x, as x approaches 1. Well, x is approaching 1. So let's look at the left one, the limit of 2x as x approaches 1. And look at this one, the limit of x to the power of 4 minus x squared plus 2 as x approaches 1. Let's evaluate those. This gives you 2. This gives you 2. Because the two are identical, then the limit of g of x as x approaches 1 is also the same by, you have to write down by what? By the squeeze theorem. If you don't write by the squeeze theorem, it's really wrong. I want you to know that. Okay, we want to prove this. When you come across a case like this, I want you to know that anytime it involves a sinusoidal function, you know that the value of sine and cosine, the minimum is -1, the maximum is 1. You know that, okay? For that, you want to start with that approach and then make it look like this expression. This is the trick that is used, okay? So we know that sine of theta is between -1 and 1. Now, whatever theta might be, in this case, theta is 2 pi over x. So sine theta, let me just write sine theta. We know sine theta is between -1 and 1. Theta, in this case, is 2 pi over x. Now, if I square that, please understand when you square it, it is between 0 and 1, not between 1 and 1. Let me make sure everybody understands. When you go from negative to positive, you can't just square this, okay? If both numbers are positive, let's say from 1 to 5, then you can square both sides. But this is not the case. Because when you square it, it becomes positive, but can still be 0, yes. I mean, for example, sine of 0 is 0. So it changes this 1, when you square this 1, but this one, you want to change it to 0. Now you want to make it look like this. So what is missing here? Well, look at this brackets. What's missing? Number 1. Let's add 1. Okay, go back. Go back. So we are in good shape so far. Bracket is taken care of. What's missing? Square root of x. Well, let's multiply everything by square root of x. Okay, and by the way, square root of x is always non-negative, remember that, especially when x is approaching 0 from the right. Now, let's take the limit, okay, of all sides. This one we can, this one we can, as x approaches what number? Take a look at what we want, 0 from the right. This one gives you 0. This one is going to give you 0. Therefore, by the squeeze theorem, the middle one gives you the same answer, 0. And that is the technique, that is the trick involved. I hope everybody's following that, okay? So by the squeeze theorem, we get to the same answer. We want to find the following limit. And we really should remember the one-sided limit, okay, everybody, that exists. And the reason you want to discuss the one-sided limit because you see absolute value. You have two choices. You can simplify this class first and then approach it, or you can start with x approaching -6 from the right and left. So let's do that. I want to quickly show you both ways. If x approaches -6 from the left, what happens? Again, I'm reminding you of absolute value of x by definition is x. If x is positive or non-negative for that matter, minus x. If x is less than 0. So therefore, because it's from the left and it's negative, you replace the absolute value with a negative sign. Then x plus 6 cancels out x plus 6, and you get -2. On the other hand, if we approach it from the right side, we just drop the absolute value, they cancel each other, and we get to +2. They are not identical. Therefore, the limit doesn't exist. Why? The one-sided limit. The limit doesn't exist because the one-sided limits are not the same. This is one way to write that. Another way of writing it is this class. If you, let me use a different color. If you said f of x is 2x plus 12 over the absolute value of x plus 6 equals 2x plus 12 over x plus 6, you can drop the absolute value, okay, if what? If x is larger than or equal to -6, and it's 2x plus 12 over negative of that, if what? If less than, x is less than -6. And if you do that, this simplifies to 2, this simplifies to -2, and you can deal with this to take a limit, okay? In other words, either way you have to look at it from one-sided limit. One way is the simplified version, one way is not. Finally, let's take a few minutes to discuss this, okay? Let me quickly read this for you, class. This symbol, it's whatever, this is epsilon, whatever the value of epsilon larger than 0. This is, there is delta larger than 0. Delta, epsilon, delta, they are both extremely small. So whatever the value of epsilon larger than 0, there is a small number delta larger than 0, such that, this is read such that, if absolute value of x minus a is less than delta, meaning what? Meaning the distance, okay, that x and a has is extremely small. When we look at absolute value of x minus a, we are looking at the distance between x and a, okay? So a in this graph is number 3. X is some number on the side, left or right. As long as the distance between that x and this 3, or in this case, x and a, is less than delta. Because in an absolute value, it can be to the left or right of it. Then the result is then the absolute value of f of x minus L. What is the absolute value of f of x minus L? The distance between f of x and L. What is f of x? Is the y coordinate. In this example, the y coordinate is 5. The distance between the y coordinate 5, okay, and f of x, I would say, and the limit 5, the limit is 5. The distance is less than some other value, not delta, but epsilon, where epsilon is also extremely small. That's the concept, which means if the x, in this case, x equals a is within delta to the left and right, then f of x, the limit of that is within epsilon. It can't go more than that. That's the idea for that. So the limit of x as x approaches 3 equals 5 means f of x is close to 5 when x is close to 3. And that's the idea, okay, behind this. I hope everybody is comfortable with the concept, okay? So this is the precise definition, okay? Let f of x be a function defined on some open interval that contains a except possibly at a. Remember, the a is not important. We are coming at a from the left and right. We say the function has a limit at a if, okay, the limit of f of x, you know, as x approaches a is L, if for every small number, epsilon larger than 0, there's a number, delta larger than 0, okay, extremely small also, such that if distance between that number and a is less than delta, then distance between the f of x and L, this is L class, let's change this, this is L, okay, this is L, is less than epsilon, okay, and basically we are within the delta of A and within the epsilon of L. That's the idea. So it maps a point, okay, if this is A minus sigma, A plus sigma to a point within L, L plus epsilon and L minus epsilon. That's it. All right. Let's quickly look at this example. You really don't need to do much. You can just look at the graph and answer it, class. I want you to know that, okay? You can look at the graph and answer it, and that's fine. But anyways, let's go through the process and then the easy way out. The easy way out, it says, use the graph to find delta such that if the absolute value of x minus 3 is between 0 and delta, f of x minus 2 is less than 0.5. So take a look at, if we were to go with the graph, you see this is number 2, this is within 0.5, so this is 1.5 to 2.5. That's what we want. We want somewhere in between, anywhere is fine. What should we pick for delta? As you look at the graph, you look at this distance, and again, I want to discuss the graph first. You look at this distance, class, from 3, and you look at this distance from 3. I hope you realize that we have to pick something to work out. If we pick this distance, 3.8 minus 3, works for the right, but for the left it doesn't because it goes beyond the 2.6. I hope you see that. But if we pick the distance between these two, so between these two is 0.8, between these two is 0.4. The 0.4 works for the left, 0.4 also works for the right, okay? But 0.8 doesn't work for the left. Therefore, how do you pick the value? The smaller of the two. So from the graph, you already know this distance is 0.4, this distance is 0.8. You pick a maximum value should be 0.4. So anywhere, any number less than 0.4 will do the job. If we were to go through the process, okay, we start with always f of x minus L less than epsilon, okay? We already get there. We already see it from the graph, but the process of numerical analysis is this, okay? I hope you remember the absolute value means sandwich between the two numbers. I hope you remember that. I'm going to write that for you, class. When absolute value of x is less than k, assuming k is positive, x between minus and positive k. If it's negative, it doesn't exist. There's no solution. And so you add the 2 to both sides, and it gives you the same numbers that we have here, 1.5 and 2.5, okay? So f of x is between that, and as you can see, x is between those two numbers. So you really don't even have to go through that because you're looking at the graph. Therefore, delta has to be one of these two, but it has to be the smaller of the two. So take delta to be the minimum of these two numbers, the smaller of the two numbers. Why? Again, pick 0.8. Does it work for the right side? Yes. Does it work for the left? No. Pick 0.4. Does it work for the left? Yes. Does it work for the right? Yes, it's less than that. So you end up somewhere here. Okay, so any smaller number will do the job. And that's the idea. I want to quickly look at one example from A to Z. And it's a tedious process, but it's pretty straightforward. I've done it in my PowerPoints, and I'm going to repeat that here quickly. If we are interested in proving this, I always write this for you so you have it. Whatever epsilon larger than 0, there is delta larger than 0, such that if absolute value of x minus a is less than delta, that means the distance between the two is less than delta. Then absolute value of f of x minus l less than epsilon, that means the distance between the coordinate on the y-axis and the limit is less than epsilon. Okay, and so we're going to do the write out. That means we are going to write exactly what we can extract from this. So we're going to write this. How do we write this? Well, what is a? A is 3. What is f of x? 4x minus 5. What is L? 7. Just write it. So right from here, I hope you can see the translation from here to here. Okay. And we always start with f of x minus L. We start with the second part. That's how the proof works. So write this part. Absolute value of 4x minus 5 minus 7 less than epsilon. And if you combine these two, you get minus 12. And I can take out the 4. Okay. And now I'm going to compare to the first part to this part. I am comparing, and I notice that this part is identical. What does it mean? If I divide this one by 4, I get to this left side. So that gives me a choice, because the idea is to find a relationship between epsilon and delta. So I divide by 4, and when I divide by 4, the left side, they become identical. And that shows me now this should be the choice. Practically, you're done. So delta is the same as epsilon divided by 4. That would be the choice. And of course, anything less than that will do the job, okay? So now you practically reverse this class. You reverse this, that's all, okay? You reverse the process. So given epsilon larger than 0, choose delta equals epsilon divided by 4. That would be the choice. Now we are going to do the proof by showing that this delta works by reversing the process, okay? Reversing the process. How? Start with this. If absolute value of x minus 3 is less than what? Delta, and we are choosing delta to be epsilon divided by 4. If we are, okay, we start from here. Now let's multiply by 4. Let's multiply by 4. What happens? Now this is epsilon. Now what is this? I can take the 4 inside, I get 4x minus 12. And remember what I want. I'm going back. Remember that. I'm going this way, class. I am going this way. So I got here. Now I can, because I know it looks like that, I'm going to write it. Class, you don't have to reinvent anything. Just go back. So I am here, so I'm going to go back. I say this looks like this. And now what do? I put the first one and this last one together. I put this one and this one together. I put them together and I write them. And I have exactly what I wanted to prove. That if absolute value of x minus 3 is less than delta, then absolute value of 4x minus 5 minus 7 is less than epsilon. Now, what is that? Remember, we are here now, class. We are here. How did we get here? So we are, okay, so let's go back here, and we come here. Now, how did we get here? From here. So now here's the last step, going back to the very last one. okay? And that is the proof for this limit. The limit of 4x minus 5 as x approaches 3 equals 7.